Hi, and welcome back to Dr. V's Chemistry Webcast. The focus for today is writing electron configurations. Here's what I'd like to accomplish in this webcast. I want to introduce you to the 3 rules that are used to write electron configurations and show you 3 different formats that are commonly used to write them. We'll tie this into the idea of valence electrons and do a number of practice problems as we work through all of this. I recommend keeping a periodic table handy so that you can do the practice problems right along with me and get really good at writing electron configurations. Electron configurations are a way of describing the arrangement of electrons in atoms. It's kind of like the address for the electron. So instead of the town and the street and the house number, it's energy levels and sublevels. And these are really useful in allowing us later to explain patterns of reactivity. So let's jump right in and start with that first rule. The first rule for writing electron configurations is called the Aufbau Principle. And the Aufbau Principle tells us that when we're writing a ground state configuration, the lowest energy arrangement, we fill our orbitals in order of increasing energy. We're going to start with our lowest energy orbital, which is the s orbital in energy level 1, fill that up, then go to energy level 2, and so on. All right. So once the s orbital in energy level 1 is completely occupied, we'll go to the s orbital in energy level 2. After the 2s orbital is filled, we can go to the 2p sublevel. After 2p, we can go to 3s. And when we have a diagram like this, it's fairly easy to generate the sequence. 1s, then 2s, then 2p, then 3s, then 3p. And that would actually be the first 18 electrons, which is great. After 3p, it gets a little harder to predict the sequence, and we'll come back and talk about how we can know that. Early on, at least for the first 18 electrons, you can just remember 1s, 2s, 2p, 3s, 3p. One thing I do want to point out is that p orbitals come in sets of 3. So the p sublevel has 3 orbitals. If you look at the 2p sublevel in the diagram, there are 3 boxes, similarly for 3p and 4p. All right, so that's an important thing to remember. Students sometimes forget that. All right, in general, we see that s orbitals have lower energies than p orbitals, which are lower in energy than d orbitals or f sublevels for that same energy level, so that number in front of the letter. Like I said, the filling sequence gets more complicated as we go on. I do want to remind you that d sublevels contain 5 orbitals, and that's shown here for the 3d sublevel. F orbitals aren't shown here, but they have 7 f orbitals in an f sublevel. So that's something we need to remember when we get up to those higher energy levels. So at this point, we can write an electron configuration for hydrogen. All right, now we know hydrogen has 1 electron and has to go in the lowest energy orbital, which would be the 1s orbital. So we'll do this with orbital notation, which involves arrows and boxes. I don't always draw boxes because they take me a while. I usually just draw a line. That's fine. I label it 1s. All right, and I've got 1 electron to put in here, so I'm going to draw 1 arrow. I chose to draw it up. I could have drawn it pointing down. It's all fine. What matters is that there's 1 of them. All right, so this is my orbital notation. There's 1 electron in that 1s orbital. If I want to do spectroscopic notation, I want to give the same information, but the format's different. Instead of arrows, I use superscripts to tell me how many electrons are in that sublevel, and I would write 1s1. And that's how you say it, 1s1. There's 1 electron in the 1s orbital. 2 ways of saying the same thing. All right, well, that's great, but I can't do anything more until I have another rule. The next rule is called the Pauli exclusion principle. And when Wolfgang Pauli presented it, he did it in terms of quantum numbers. He said no 2 electrons in the same atom can have identical sets of the 4 quantum numbers. And if you already know quantum numbers, this is just fine. And if you haven't done quantum numbers, this isn't going to make much sense. So I'm going to explain it in a different way. Electrons have a property called spin. And this doesn't mean actually that they're rotating around an axis, but that's a convenient analogy to help us visualize it. So here it shows an electron spinning clockwise and one spinning counterclockwise. It's sort of a up and down. It's an opposite situation. There are 2 possibilities and they're opposite of each other. Whatever those are, they're opposites. So you can think of it as up and down, clockwise versus counterclockwise. It has it written here as +1/2, -1/2. That's the quantum number approach. they're opposites. That's really what's important here. So we can recast the Pauli exclusion principle in terms of this. We can say 2 electrons may occupy the same orbital, but they must have opposite spins. This is a little more manageable if you haven't done quantum numbers. So this now enables us to write a number of additional electron configurations. Let's go on and do that. An analogy for this would be if you've got 2 siblings sharing a room. Someone's got the top bunk, someone's got the bottom bunk. Okay, so we can go on and write an electron configuration for helium, and we're going to do orbital notation and spectroscopic notation because we can. So helium has 2 electrons, right? And so starting with our lowest energy orbital would be the 1s sublevel, and I can put 2 electrons in there if they have opposite spins. So I'm going to write 2 arrows, one up, one down. And that's what I need to write for my orbital notation. Spectroscopic notation, I would write 1s2. There are 2 electrons in my 1s sublevel, and that's what we can do for helium. Lithium has 3 electrons. We can do the same kind of thing. Now I've got 3 electrons. Obviously, they can't all go in the 1s sublevel, but 2 of them can go in the 1s sublevel, and my 3rd electron would have to go in the next one up, which would be the 2s sublevel. There's 1 electron there. Now I drew it with an arrow pointing up. I could have just as correctly drawn an arrow pointing down. That's really what's important, is that there's 1 electron there. So in my spectroscopic notation, I would write 1s2, 2s1. If we go on and look at beryllium with 4 electrons, right, I can completely fill my 1s sublevel, and I can completely fill my 2s sublevel. So I would write 1s2, 2s2 for my electron configuration. And then we can go on to boron with 5 electrons. I can do 2 in the 1s sublevel, 2 in the 2s sublevel. The next sublevel after that is the 2p sublevel. I have to remember it's got 3 orbitals, so I have to draw 3 lines for the 2p sublevel, and I put 1 electron in one of those. And so I would write for my spectroscopic notation 1s2, 2s2, 2p1. Okay, great. But I can't go any farther until I learn the 3rd rule. So let's go ahead and do that. The 3rd rule is called Hund's rule, and it applies to the P, D, and F sublevels. These are the sublevels that have more than 1 orbital in the sublevel. And we say that the orbitals in these sublevels are degenerate. They all have the same energy. So the p orbitals in sublevel 2p all have the same energy. The 5d orbitals in a 3d sublevel all have the same energy, and so on. So the rule says, for these p, d, and f sublevels, I have to put 1 electron in each orbital, all with the same spin, that's what I mean by spin aligned, before pairing any electrons. 1 in each before you pair. So, if I have a 3p sublevel, and I have 3 electrons that need to occupy this sublevel, I put 1 in each orbital, all with the same spin, before I pair anybody. All right, 1 in each before you pair. If I only have 3, that's where I stop. If I drew something like this, where I have 3 electrons, but I've got 2 of them paired and an empty p orbital, that's not correct. That's not following Hund's rule. 1 in each before you pair. And now that you know Hund's rule, you can write electron configurations for all of the atoms. We need to practice, but we've got all the information that we need. So, an analogy for Hund's rule is if we're looking at, say, a 3-bedroom apartment. If there are 3 people who live in the apartment, they each get their own room. If 4 people live in the apartment, one room will have 2 occupants and the other rooms will be singly occupied. Right? So if you can have your own room, you'd rather have your own room. You only share if there's more occupants than there are bedrooms. It works. So we can go and write an electron configuration for carbon, all right, which has 6 electrons. We can fill up the 1s sublevel, and we can fill up the 2s sublevel. Our last 2 electrons have to go in the 2p sublevel, 1 in each before you pair. So this is what I end up with. All right, so that's my orbital notation. For my spectroscopic notation, I'd write 1s2, 2s2, 2p2. For nitrogen with 7 electrons, again, I can completely fill the 1s sublevel and the 2s sublevel. And then in the 2p sublevel, I'll have 1 electron in each, because I had 3 electrons to occupy that 2p sublevel. So what's nice about the orbital notation is that it shows you half-filled sublevels and half-filled orbitals, which the spectroscopic notation can't show. So a lot of times you'll find that your chemistry teacher is going to ask for arrows and boxes because they want to see if you understand and can apply Hund's rule. Spectroscopic notation for nitrogen, of course, would be 1s2, 2s2, 2p3. We can go ahead and do neon, which has 10 electrons, 1s2, 2s2, 2p6. So all of the orbitals are completely filled. All of the sublevels that are occupied are completely filled. And that's a hallmark, actually, of the noble gases. All of the sublevels are completely filled. For sulfur, we can go beyond, right, into period 3 and continue the same process, right, with 16 electrons. We're going to start off with 1s2, 2s2, 2p6. All right, that's 10 electrons. We can do 3s2. That gives us a total of 12 electrons represented so far. And our last 4 electrons would have to go into the 3p sublevel, which of course has 3 orbitals in it. So I've got the 3 lines, 1 in each before I pair. 1, 1, 1, and then I'm going to pair it up. I can pair up the electrons in any one of the 3 orbitals, right? But I see from this electron configuration that sulfur's got 2 unpaired electrons. And my spectroscopic notation would be 1s2, 2s2, 2p6, 3s2, 3p4. So let's talk about mistakes. Students sometimes do make mistakes when writing electron configurations, and you should be able to determine what rule's not being followed and then how to write it correctly. So if we look at this electron configuration, what's wrong with it? Well, it doesn't follow the Aufbau principle. The 2s sublevel is not completely filled, and yet I've got electrons occupying the 2p sublevel. So that's not typically what we would write for a ground state electron configuration. It could be maybe an excited state where one of the electrons has gotten energized and moved to a higher energy level. But it's not a correct ground state configuration. It would be better to write it 1s2, 2s2, 2p1. What's wrong with this electron configuration? It starts off okay, but then I look at that 3s sublevel and I've got 2 arrows pointing down. That doesn't follow the Pauli exclusion principle. They don't have opposite spins, so we need to correct that, right? 2 electrons can only occupy the same orbital if they have opposite spins. Okay, what's wrong with this electron configuration? Well, I'm looking at that 2p sublevel, and it's clearly not following Hund's rule, right? I should have 1 electron in each orbital with spins aligned before pairing any electrons, and I don't have that. I should have 3 half-filled orbitals for the 2p sublevel. There's one more of these. What's the mistake here? All right. Well, the sequence looks fine. What's wrong with it? Well, the problem is that the p sublevel should have 3 orbitals, and it's only showing 1, right? So that's clearly a problem. This is actually a fairly common mistake among students who are just learning to write electron configurations. So we need to make sure that we put in the complete set of p orbitals for the 2p sublevel. All right, the 3s sublevel isn't occupied yet. So, all right, well, we've got all the rules down. We've seen 2 out of the 3 formats, but we can't write electron configurations beyond 18 electrons. We need to talk about that filling sequence and what happens after 3p. So it does get more complicated, and what this visual involves is a mnemonic device that we can use to generate the filling sequence after 3p. All right, so what it is it lists the orbitals in columns, and then there are arrows coming in at diagonals, and if we follow the path of the arrows, we can generate the filling sequence that we need. So that we see from the arrows after 3p, we get 4s, and then 3d, and then 4p. This isn't something that you can really memorize. You really need to have a memory device to help you generate this. And that's what I'm actually going to do on the next slide, take you through that. As an analogy, it's kind of like a high-rise building, right? Where the rents are higher on higher floors. If the view is better, they can charge you more. But also the size of the apartment has an effect on the rent. The more bedrooms you have, the more the rent would cost, which also seems reasonable enough. But the net effect is that a 1-bedroom apartment on the 4th floor has a lower rent than a 5-bedroom apartment on the 3rd floor, which isn't immediately obvious and yet doesn't seem so outrageous either. So that's a nice analogy for the filling sequence as it gets more complicated. So students find if they can generate this mnemonic on their own, they're much more likely to use the correct Aufbau filling sequence. So here's how you generate that diagram. We're going to make a column for all the s orbitals and all the energy levels. So 1s, 2s, 3s, 4s, 5s, 6s, 7s, and we just list them vertically. And then we're going to make a similar column for the p sublevels, but we don't have a p sublevel until energy level 2. So we'll start with 2p and fill that down. 2p, 3p, 4p, and so on. You don't need me to say all of those. And then we'll do another column for the d sublevels, all right? But d's don't show up until energy level 3. And then we'll do a column for the f sublevels. They don't start until energy level 4. So we write these columns down, and then we can start with our arrows on a diagonal starting with 1s. All right, so the 1s orbital is the one we fill first, and then we put in our next arrow, and that takes us to 2s. And our next arrow goes from 2p to 3s. And then we put in our next arrow, and that's 3p to 4s. So now we can start talking about the filling sequence being a little more involved. And after 4s, our next arrow takes us 3d and 4p and 5s. And then another arrow will get us to 4d and 5p and 6s. And another arrow, finally the 4f's to 5d to 6p to 7s, and so on. And we can do, we can just keep generating this, 5f to 6d to 7p, and keep generating the list as far as we need to. That's a lot of electrons, but that's the filling sequence, and it's one way to generate the list. So if we've got that, and you should practice generating it on your own, we can now write electron configurations for larger atoms. So we could do chromium, for example, which has 24 electrons. So we'll start with 1s, 2 electrons in there. We'll start with 2s, another 2 electrons. The 2p sublevel, 6 more electrons, so that's given us a total of 10. And then the 3s sublevel gets filled, and the 3p sublevel gets filled. After 3p, if we look at our diagram, comes 4s. We'll fill that up completely. And then after 4s, our arrow filling diagram says 3d is the next sublevel. Remember, d orbitals come in sets of 5, and we have 4 electrons to place in them. So we have 4 half-filled orbitals in the 3d sublevel. I do recommend when you're doing electron configurations for these larger atoms, definitely count your arrows and make sure all the electrons are represented that need to be represented. Now we can also use the periodic table to generate the filling sequence. The periodic table is actually a giant mnemonic device for electron configurations. It helps to know the block arrangements of the periodic table. So groups 1 and 2 can be referred to as the S block. Groups 3 through 12 are the D block. Groups 13 through 18 are the P block. So notice the P block elements, all the electron configurations end in P. For the D block, all the electron configurations end in D. For the S block, they all end in S. We've got the lanthanides and actinides can be referred to as the F block. And the other thing to notice about the periodic table is that the period number refers to the highest occupied energy level. So we can use this to actually generate the filling sequence. If you have a periodic table, you can just run your finger from left to right, and we can generate this. You're going to want to practice it. So let's go through it together. All right, so we start always with 1s. We'll fill that completely. After 1s comes 2s, and then 2p, and then 3s, and then 3p, and then 4s to 3d to 4p as we move from left to right. After 4p comes 5s, and then 4d, and then 5p. And after 5p comes 6s, and then we jump down to the F block. We have 4f, and then back to 5d and 6p, and then 7s, and then 5f, and 6d, and 7p. It's a lot. But if you know how the blocks are arranged and you practice, you can actually generate the filling sequence right from the periodic table. The other thing I wanted to mention was that you can count over the number of columns in the block, and that will tell you how many electrons are in that sublevel. So really, it's a giant mnemonic device for electron configurations, and you can do this very, very quickly. So let's do some more practice. Okay. But we're going to introduce another notation. I said there were 3 notations for electron configurations. The last one is called noble gas notation. We can use a noble gas, a group 18 element, to represent the inner or core electrons, and then show the electrons that are beyond that. So it has to be a noble gas. It has to be a group 18 element. Remember, these have all of their occupied sublevels completely filled. Let's do an example. If we do carbon, we had written an electron configuration for carbon earlier in the webcast, 1s2, 2s2, 2p2. So the first 2 electrons of carbon, all right, in the 1s sublevel, correspond to the 2 electrons of helium. So what we can do is write the symbol for helium in square brackets to represent those electrons, and then write the electrons outside of that using something like a spectroscopic notation. So helium 2s2, 2p2. Notice we don't use any arrows in this notation, right? And obviously you need to pick a noble gas that has fewer electrons than the element you're interested in, or it doesn't work. Like I said, it's got to be a noble gas. So let's do some more practice with this, all right? So for magnesium, right, which has 12 electrons, right, the noble gas we would want to use would be neon with 10 electrons. So we would write neon in square brackets, and then, right, we're in period 3, and we're in the S block. We're the second column of the S block, and so it would end as 3s2. Alternatively, you could write out the spectroscopic notation and just take away the stuff that corresponds to neon and replace that. If we wanted to write an electron configuration for iron, which has 26 electrons, right, we would use argon as the noble gas. You kind of go up one and over, all the way over to the end, right? So we could represent the first 18 electrons with argon, write that symbol in square brackets. What follows after that? Well, we're in period 4 in the D block, so it would be 4s2, 3d6. Remember, the D's are always 1 behind, all right, and the F's are always 2 behind. Let's do a little more practice. This is really handy if you have very long electron configurations. It also emphasizes the electrons that are outermost in the atom, and there are times when we want to do that. So if we're looking at iodine, which has 53 electrons, we would use krypton as the noble gas. And we're in the P block for iodine, and we're in period 5, so it starts as 5s2, 4d10, and then 5p5. We're 5 columns into the P block. We'll do one more example. Let's look at bismuth with 83 electrons. Right, we would use xenon as our noble gas. We'll write that in square brackets. And then we're in period 6 in the P block. So we're going to start at 6s2, and then we have to jump down to the F. We'll have 4f14, back to the 5d10, and end as 6p3. Okay, so I wanted to segue into valence electrons. Valence electrons are defined as the outermost s and p electrons in an atom. We're not going to include d electrons or f electrons as far as that goes. There is a more nuanced definition, and for those of you taking AP chemistry or college level chemistry, your instructor may have talked about that more nuanced definition. That's outside of the scope of what I want to do right now. So the outermost s and p electrons are defined as the valence electrons. These are the ones that actually get involved in chemical bonding and reactions. If we look at carbon again, all right, we had written its electron configuration as helium 2s2, 2p2. There are 4 electrons in the outermost s and p sublevels, right? And there are 4 valence electrons in carbon. So you can figure this out from an electron configuration, and it's pretty easy to do. We can also do it right from the periodic table. All right, main block elements, or S and P block elements, can have up to 8 valence electrons. And we can find the number of valence electrons from looking at either the group number or the group number minus 10. So for our alkali metals in group 1, they have 1 valence electron. For our group 13 elements, there are 3 valence electrons. For our group 15 elements, there are 5 valence electrons. For our group 18 elements, there are 8 valence electrons with the exception of helium. Since helium only has 2 electrons, that's what it's got. It can't have 8. So we can very easily figure out the number of valence electrons just from looking at the periodic table. All right. We're going to say for now that D block elements have 2 valence electrons. Again, there's a more nuanced definition here, but it's outside the scope of what I want to accomplish today. All right, so if your teacher has told you to do something else, then you should do that. But we can also use this to represent Lewis dot diagrams, all right, where we have 1 dot for each valence electron around the symbol for that element. So if we go back to carbon with its 4 valence electrons, we would have 4 dots around the carbon symbol. And this gets very handy when we start talking about bonding and reactions, being able to explain that. So we'll do some examples right now because we can. All right, so for magnesium, it's a group 2 element. It has 2 dots. For nitrogen, it's a group 15 element. Look at your periodic table. So it should have 5 valence electrons, and we'll put 5 dots around the symbol. If we're looking at sulfur, it's a group 16 element. So we should have 6 valence electrons and 6 dots. And we'll wrap up with aluminum. It's a group 13 element, and therefore it should have 3 valence electrons and therefore 3 dots. Wow, we've really done a lot. I think we're ready to wrap up. So we learned to use the Aufbau Principle, the Pauli Exclusion Principle, and Hund's rule to write electron configurations. We learned 3 notations: orbital notation, spectroscopic notation, and noble gas notation for electron configurations. And we learned about valence electrons and used them to write Lewis dot diagrams for our main block elements. We did some really good work here. I encourage you to come back, subscribe today to my channel, and keep learning chemistry.